Great. So let me get started then. So I say I very much enjoyed Katie's talk, and I'm going to just add a few more thoughts along the lines that she described. Now, I should say that I am aware that, well, first of all, the topic of my talk is the small-scale problems of CDM, which is what the organizers asked me to talk about. And I am aware that many of you are experimental physicists looking for dark matter. This is a talk on astrophysics, but don't worry, I think astrophysics is good for your health. But at any rate, just to make sure, let me begin with my take-home messages. And these are in the form of two pleas. One for experimentalists, which is please keep looking for CDM. Don't be discouraged. It's not easy, but it is pretty likely that CDM is out there waiting to be discovered. Otherwise, the universe doesn't make any sense at all. And my other take-home message is to theorists, another plea: please do not invent new particles to solve small-scale crises of CDM. If you have other reasons for a new particle, by all means, but not to solve a crisis that, as I will show, doesn't really exist. Right, so what is this small-scale crisis? Well, it's formulated often as 4 problems that I've listed here: the missing satellites, too big to fail, plane of satellites, and core cost problems. I'm going to run through these relatively quickly. I should just point out that the first of these, the missing satellites problem, is an interesting thing because it was a problem that was solved before it actually became a problem. I'll justify that in a minute. And actually, interestingly, the same is true about the fourth. These two became problems after the solutions were known. Now, so the missing satellites problem. Well, these are a very old picture of simulations of dark matter halos carried out, what is it now, nearly more than 35 years ago. And you can see these are galactic halos, and you can see there how they form by mergers of substructures that, in fact, we can now follow in a much more precise way with, whereas those simulations, the halos had 4,000 particles or so, we are now able, like, for example, in this Aquarius project, to do simulations of galactic halos with 1 billion particles, where you now see much greater detail all the result of that hierarchical merging process. Now, so around the end of last century, Ben Moore and collaborators and Anatoly Klipin and collaborators pointed out that the number of satellites that we see in the Milky Way, here's the number as a function of some measure, as the circular velocity, some measure of the size or the mass, if you like, of the object, that the number of satellites that you can see here, there was about 10 known at the time, is much smaller than the number, by at least 2 orders of magnitude, than the number of subhalos that are predicted in simulations like those here on the left. So it's this disparity that you can see here as well, that is what is known as the missing satellite problem. So here is that halo that I showed you before. As you can see, there are thousands, hundreds of thousands of small objects, whereas we know that the Milky Way, we have so far discovered only 55 satellites, which is, of course, a lot fewer than the number of subhalos here. So these are some of those satellites. And the missing satellite problem then is the disparity between the observed relatively small number of satellites and the huge number of subhalos that we see in the simulations. Now, there isn't just, you might say, well, maybe there's more. Only 55 have been discovered. As I said, around the turn of the century, only 10 were known. Now we know up to 55. What if there are many more lurking around? Well, the answer is no, because there are more, of course, that we haven't discovered, because the surveys don't cover the whole sky, and also they're not, they have a flux limit. However, we can estimate from what we know, which is quite a lot, what they should be there just by essentially extrapolating, knowing the selection function and other experimental details. We can calculate how many satellites the Milky Way actually has. And that's work that was the thesis of my student, Oliver Newton. And here you can see that to magnitude 0, which corresponds to about 1,000 stars or so, we expect about 125 satellites. So we know 55, there's still quite a few to be discovered, but 120 is nowhere near the number that is needed to solve this missing satellites problem. So the problem as formulated is certainly there, but the answer to the problem is not look for more satellites. The answer to the problem is that most of these subhalos are never able to make a galaxy. So, and we've understood for a long time why that is the case. And that's why I say this problem was solved before it became a problem. It's only a problem if you forget about the physics of galaxy formation. In fact, these relevant physics I'm going to describe in a minute. In fact, they were well understood already at the beginning of the century. This is work from the thesis of my former student, Andrew Benson, but other people have had similar thoughts before. So what's plotted here is the number as a function of luminosity or magnitude. This is magnitude 0, corresponding to about 1,000 stars. These are faint, these are bright. And in 2002, only 11 satellites were known, shown here by the red line. And these are the models that Andrew Benson calculated using something called a semi-analytic model of galaxy formation. And you can see that there's a lot of scatter in the theory, but in the models, but they agree pretty well with the expected number of satellites. Although we'll come back to this, Andrew predicted that there should be a population of ultra-faint satellites that hadn't been discovered yet in 2002. So let me tell you a bit about the physics behind this. And it's relatively straightforward physics of galaxy formation. So we know that there are two phases of galaxy formation. Katie talked about some of those ideas a few minutes ago. Galaxy formation begins here during the dark ages, during what I call phase 1, which is when the hydrogen is neutral. And then eventually the hydrogen gets reionized, and that in fact causes galaxy formation to stop temporarily, and then it resumes after the universe has reionized in a slightly different form. So that's phase 2. So let me just tell you a little bit more detail about what's going on. So this is all described in a recent paper by with my postdoc, Alejandro Benitez Lambay. And although the ideas go back 20 years or longer, I think in this paper you can see it all put together, together with some new thoughts on how these things work. But the main point is that when the hydrogen is neutral, before reionization, in order for gas to be able to make a galaxy, first has to cool into a small dark matter halo. But if actually, paradoxically, hydrogen only cools if it gets heated first, which it does through shocks. So only gas that is heated by collisional, ionized by collisional ionization to temperature greater than 7,000 Kelvin, only that gas is capable of cooling to make stars. And that happens if the halo in which the gas is cooling is more massive than about 10 to the 8, 4 times 10 to the 7, and it depends on redshift. So there's a critical before reionization mass shown here in orange, and if the halo is below this critical mass as a function of redshift, it's never going to be able to cool gas and make stars. So it has to protrude above this orange line in order to be able to make stars. However, about redshift 10 or 9 or something like that, the hydrogen reionizes, and now that heats up the gas to about 20,000 Kelvin. And now gas is only able to cool if the depth of the potential well is enough to be able to support the cooling of this gas. And so the effective virial temperature of the halo has to be larger than about 20,000 Kelvin, corresponding to this next critical line for the gas to be able to cool. So a halo, if it's before reionization, has to be able to cross this line. If it's going to make a galaxy after reionization, the critical mass goes up to this black line here. So it's all pretty simple, basic atomic physics that determine whether or not a halo is going to be able to make a galaxy. Now let me show you examples of 2 halos, one that made it and one that didn't, here shown in brown. So the 2 of them ended up at redshift 0 with the same mass, about 3 times 10 to the 9. So they have the same mass today. But this one, the first one here, This one got lucky, and before reionization, it crossed over the critical mass, so it started making stars here, and then it had another go later on when it went above this other critical line. So this one ended up making a galaxy. But this other one, which has the same final mass, this never crossed either before reionization or after. It never crossed the black line. It never crossed the critical mass. It never managed to cool gas to make a galaxy. And so this ended up as a completely dark halo. So here are some more examples of halos depending on the final mass. So if the final mass today is 10 to the 8, well, none of these ever make a star. So they're all dark. If the final mass is a few times 10 to the 8, well, some do and some don't, depending on whether they cross this magical line. If they're 10 to the 10 solar masses today, they all make it, and they all make a galaxy. So we can define something called the halo occupation fraction, which is the fraction of halos of a given mass that can host a galaxy. Above 10 to the 10 or so, they all host a galaxy. This fraction is 1. Below 10 to the 3 times 10 to the 8, they're all dark. And then there's a relatively sharp transition where, like the example I showed, where some halos manage to make a galaxy and others don't. So this is the basic physics that underlies these calculations by Andrew Benson and many others. Now, I'm going to come back to this plot later. This is actually the mass function of dark matter halos. Now, you've never seen a plot like this in the subject, I'm sure, because there are 25 orders of magnitude here. And I'm going to tell you how this was calculated in a few minutes. But this is the definitive mass function of dark matter halos in CDM from the free streaming cutoff mass, the mass of the Earth around here, all the way to galaxy clusters. The reason I'm showing you this now is to point out that it's only this very small fraction of the halos that actually manage to make a galaxy, right? So you know, it's many orders of magnitude more halos that never managed to make a galaxy. So most of the halos in CDM in the universe are actually dark. Only a chosen few managed to make a galaxy. Now, so these are all analytical arguments, but we can now do very impressive hydro simulations where we can try to do the physics as realistically as possible. One example is this EAGLE project that many of you would have heard about. There's others like Illustris and many others, but this is the one that I'm part of. So I will show you some results of a sub-project we did within EAGLE to simulate the local group. Here is the Milky Way, and here is M31 in a simulation, of course. And this is what you would see if you were lucky enough to be able to see the dark matter. You would see a huge number of small subhalos. The universe would look very interesting, unlike what it actually looks like, because only these are the stars in the simulation, and only a very few, a very small fraction of the halos actually manage to make a galaxy. And so that's what the universe looks like in dark matter, and this is what it looks like in stellar light, and for the physics that I just explained. And of course, when you do the quantitative analysis, we get the same answer as we did already with the analytical arguments. Here's the number of dark matter halos, many dark matter halos, a function of mass. And here are the predictions for the number of satellites. And here are the observations, and the match is just absolutely perfect. So there's no such thing as a missing satellite problem. In fact, we can even go beyond that and remember that Andrew Benson already predicted, in fact, there should be about 100 satellites brighter than magnitude 0, which is exactly what I told you is the inference of what the total number of satellites in the Milky Way is. So these are data after 2002 that showed that was indeed a population of ultra-faint dwarfs. And as I said before, we expect about 125, which is just what Andrew predicted should be there. So the bottom line here is that when galaxy formation is taken into account, CDM predicts the observed abundance of satellites. There's no such thing as a missing satellite problem in CDM. So now let me go to another, which is the second one in my list, which I think is in a way more interesting, at least the solution is more interesting. This is so-called too big to fail problem, pointed out by Mike Boyle and Colchin and collaborators about a decade ago, using, in fact, the Aquarius simulations that I showed you before. So what Mike and colleagues realized, and remember, these Aquarius simulations are dark matter only, They then plotted the so-called rotation curves. It's just the square root of GM over R as a function of radius. And for halos in the simulation. And they plotted here observational data for the satellites, 9 dwarf satellites for which these data are available. And they noticed that many of these rotation curves are too high, they're too large to be consistent with the data. And in particular, they found that the dark matter simulations make about tens of halos with Vmax, which is the maximum of the rotation curve, larger than 30 kilometers per second, but the Milky Way only has 3, which are not plotted here, is the LMC, the SMC, and Sagittarius. So this is a too big to fail problem. Why is it that the brightest galaxies, apart from these 3, which are brighter, but not plotted, why is it that the brightest galaxies don't inhabit the largest halos? Too big to fail, these halos are. Well, the answer here is, the solution to this is really interesting, and it has to do, again, with the physics of galaxy formation. You can read all about that in various papers by Til Sawala. In fact, the latest one is not here, it's in 2016. Using some of the simulations that I show you. And what happens here is quite simple. As we've seen, at high redshift, a lot of the gas cannot cool into halos, either because it's heated by reionization, and in addition to that, supernovae at early times can eject some of the gas. So what happens in a hydro simulation, as opposed to a dark matter simulation, is as the halos lose their baryons at early times. So now they find themselves at early times with less mass than they would in the Aquarius dark matter only simulation. Because they have less mass, well, they grow less, and the result is, in fact, that the rotation curves are suppressed. It's not a big effect, so it's only, here is the ratio of the Vmax in the hydro to the dark matter only simulation. It's only a 12% effect, but actually that is enough to solve the too big to fail problem that hold on. Sorry, my computer, my PowerPoint crashed. Let me bring it back up again. Sorry about that. Where is PowerPoint gone? Right. Maybe it was, oh, it's actually, what is this? Right. Let me see if this will do. This is my talk. Yeah, it is. All right, sorry. So let me go back to where I was. I don't know why I didn't, maybe it was Mike thinking about me in Texas, but at any case, at any rate, so here's where I was. Then, so what happens when you look at these exactly same rotation curves, but not in a hydro simulation? So these are actually from Apostle, dark matter only, and here's what you get with the hydro. So all these big ones are suppressed, and so we now end up with only 3, which were allowed, LMC, SMC, and Sagittarius, higher than where the data lie. So again, the solution to the to fail problem just has to do with modeling galaxy formation correctly, and then this problem actually goes away. Now, so the next problem is, this has a different solution, the plane of satellites problem. This is another interesting one, and it's been known for since 1976 by work by Donald Lindenbell, that the satellites of the Milky Way, as he used to tell me when I was a student, would come to my office and say, do you know that the satellites of the Milky Way all lie along a great plane on the sky, a great circle on the sky? In fact, the blue points here are the satellites of the Milky Way, and they are actually in a narrow plane in the Milky Way. And then later, Krupp and others found that not only are the satellites in the plane, but the 8 at least of the 11 brightest are rotating coherently. The angular momentum shown here, the direction in which they point, shown here by the triangles, is in a relatively narrow cone. So this is called the plane of satellites. And in the simulations, you can find them if you look hard enough. The red here are one of Til Sawala's simulations, and you even have some that are rotating coherently, maybe not as impressively as in the Milky Way. But the question that the fact that they can be made is clear. I mean, it has to do with the fact of the cosmic web, that satellites are accreted by filaments of the cosmic web. question is one of statistics. So for example, Ibata and colleagues tell you that, yeah, sure, you can make them, but only a tiny fraction of galaxies have alignments with coherent velocities, as we see in the Milky Way and as they discovered in this paper, also in M31. Now, trouble with this paper and many papers in this subject is the statistics are not done properly. And in particular, they forget something that we know a lot in experimental physics, which is the look elsewhere effect, or the trials factor. Now, when you take the trials factor into account, the significance of that plane we just saw is reduced by a factor of 100. This you can read about in a paper by Marius Kautun and colleagues. And in fact, it turns out that when you do the statistics in this way, then you find, in fact, that planes, about 10% of halos in lambda CDM simulations have even more prominent disks than Ibata's. So in my mind, the satellite problem is not really a problem either. Now, so let me now go on to the fourth of these problems, which is the core cusp. Now this one is another interesting one. And it goes back to the fact that it's been known for 25 years that the halos, the density profile as function of radius of dark matter halos, has these cuspy profiles, this NFW profile, where the density diverges like 1/r towards the center. So they have cusps in simulations, again, that include only dark matter. So that's the cusp. And then the question is whether nature has cores or cusps. And there are two myths in this subject. One of them is that myth one, that dwarf galaxies have cores. I'm going to show you that that's just a myth. And the second one is that all hydro simulations make cores in dwarfs. That's another myth. Now, by the way, some strange green lines just appear on my screen. Okay, Chairman, can you see those, Holger, green lines that I can see on my screen?
Yes.
You can?
Yes.
I don't know where they came from. So, all right, well, I'll just ignore them. I mean, they're just spurious lines, but so long as they don't interfere. All right, so there's two myths. One is that dwarf galaxies have cores, and the other one is that simulations make cores. And I think the two are not correct. So here is a point about the first of these issues. So what's plotted here is a measure of how much dark matter or visible matter is in the centers of halos. So this is the circular velocity. Remember, that's the circular velocity at 2 kiloparsecs. So that's a measure of how much central mass there is as a function of Vmax, which is just a measure of how massive the halo is. Now, NFW with its cusps predicts the black line here, and the red are these results from these hydro simulations, the Apostle simulations that of Till Zavala and collaborators. Now you see that here on dwarf galaxies, these are dwarfs. The simulations agree with the NFW. Here they have more mass in the center than NFW, because NFW is for dark matter only. These things have lots of stars in the center. They have lots of baryons, something called baryon contraction. And so you end up with more mass in the center that essentially the baryons of galaxies like the Milky Way. Now, so that's what the theory predicts. And the blue are observations from real galaxies, from two surveys, things and little things. And as you can see here, the vast majority of galaxies in these surveys agree with just where the doctor ordered with CDM predictions, but there are these ones that have too little mass in the center. They have a deficit of mass at 2 kiloparsecs, and these are the ones that are reputed to have a core. Right, so this is very interesting. However, of course, observers don't measure the density directly. They measure a rotation curve, and in order to infer the rotation, in order to infer the amount of mass at any radius, they need to model these galaxies. And some of these galaxies have all sorts of interesting kinematics anomalies. So what we decided to do, and this work by Kyle Oman and collaborators, was to treat some of these simulated galaxies, the green ones here in particular, pretend we're observers. We use the software that observers use, a code called Barolo 3D, and observed our theoretical galaxies, our simulated galaxies, in exactly the same way as observers would do. And here's the big surprise. When you do that, these galaxies, which have cusps, obviously they're in the cuspy line, they all appear to have cores, and this is just a result of systematics introduced by complex non-circular velocities in the H1 gas.
5 minutes left.
How many?
5 minutes.
5, okay, all right. So now, just in 1 second, suppose cores do exist. Would this rule out CDM? The answer is no. We know for a long time that you can make cores inside cusps simply by having gas collect in the center of a halo. As I just indicated, the gas becomes dominant in the center, but if it's, gas clouds have a tendency to explode, and when they do that, they can cause binding energy to be reshuffled, and the result is that you can make a core. As you can see in these very old simulations, that the cusps can easily turn into cores, and we can see that in simulations. This is work, again, by Alejandro Benitez-Lambay, and you can make cores, cusps, whatever you like, depending on the details of the hydro simulation. So, cores or cusps, I don't know. Maybe cores exist, maybe not. But if they do exist, there's no reason to throw away CDM. Now, in my remaining 5 minutes, I just want to, first of all, point out, as you all know, that CDM is one possibility. Warm dark matter, for example, a sterile neutrino is another. And as you can see here, they make very different predictions for the number of structures and substructures that you should have in the universe. So how do we count halos? Now, there are 3 ways to do that. One is gaps in streams. I don't have time to talk about this. The other one is through gravitational lensing. And the final one, which I want to talk about, is annihilation radiation. Now, because I ran out of time, I'm almost run out of time, I'm not going to tell you much about gravitational lensing, other than to say that through lensing, it may be possible to, in fact, find out these dark halos that I was talking about before, the ones that have less than 10 to the 10 solar masses. It's complicated, it's not impossible, it's doable, and maybe, according to my student, or actually my colleague, Ran Li in Beijing, with 100 systems, we should be able to discriminate between CDM and sterile neutrino. But I want to get back to this plot, which I'm very excited about. This is a project we just finished. You'll see this paper appear in Nature in a few weeks. And I'm very excited. It took us 7 years to get to this plot and the ones I'm about to show you. So what we set out to do was to simulate the entire range of masses of halos that form in CDM, all the way from the free streaming cutoff mass at about the Earth mass, all the way to galaxy clusters. And so the exciting thing, of course, is that these ones are observable by annihilation radiation, which may be, of course, one of the main ways to discover dark matter. So I'm going to run through the strategy we follow to be able to do this calculation. I'm going to run through some images first. So we start with a big cosmological simulation called level 0. Here, the objects that you see here have characteristic masses of 10 to the 14 solar masses. Here's the scale. Then we go to a region of low density, and we resimulate that with 100 times, say, better resolution. And this is what you get. Now, the characteristic mass of the biggest halos you see here are Milky Way halos, 10 to the 12. Here's the scale, and this is zoom level 1. And you can see here the structures that form. We now go to low density region, zoom level 2. The characteristic mass that you see here are the masses of dwarf galaxies. And we're now going to go here and zoom again, every time increasing the resolution by about a factor of 100. We're now at the halos you see here are the size of globular clusters, 10 to the 6 solar masses. The scale is now 150 kiloparsecs. Zoom 4. Now the characteristic mass is 1,000 solar masses. And here, this whole thing is only about 100 kiloparsecs across. Here is the next level. Now these are 10 solar masses. And here's 5 kiloparsecs. This is about 20 kiloparsecs across. And we're still going. Level 6, now the masses that you see are 1/10 the mass of the sun in these biggest objects. and the scale is now a few kiloparsecs across. We're not done yet. This is level 7, and now you're looking at objects of mass 10 to the minus 4 solar masses, about 100 times the mass of the Earth. And look, I don't have time to go into this, how the cosmic web has changed. And here's our last final zoom, where these are halos of Earth mass. The particle mass in the simulation is 10 to the minus 11 solar masses. These are resolved with 100,000 solar masses. And so these are the objects at the free streaming cutoff. Now, the first amazing result is that when you look at the density profiles of these halos over 25 orders of magnitude in mass, they're all universal and they're all well fit by NFW to an accuracy of 20%. It's just the slope as a function of radius for all the simulation levels for halos from Earth mass to galaxy clusters, and they all have essentially the same profile, universal profile, which is well described by NFW all the way to the mass of the Earth to accuracy of 20%, and or with the Ionasto profile to an accuracy of 7%. Here is the concentration mass relation, vital for understanding gamma ray annihilation radiation. And here you see what we have, that the concentrations actually drop near the free streaming cutoff. This has to do with the free streaming, properties of the free streaming cutoff. And these are all extrapolations that various peoples have made. They're all wrong, including ours from the millennium in 2007. So all the extrapolations are wrong, and actually the concentrations don't vary that much between the Earth mass and a dwarf galaxy. They range from about 30 to about 20 or so. And the scatter depends very weakly on mass. And I say this turn down is due to the free streaming limit. The only model that more or less goes through the data is Aaron Ludlow's, which is not an extrapolation. It's based on the formation histories of halos. Now, at a given mass, the halo concentration is independent or depends very weakly on environment. Here again, at various levels. These are the Earth masses over here. These are the slightly bigger ones. Remember that have slightly more concentrated than the ones at Earth mass. These are the galaxy clusters. And this is a measure of environment. And the concentrations are almost independent of environment, which is very good news because we simulated very special regions. But this is telling us that our results are in fact quite general. And here's almost my last slide, which is what I wanted to get to. Sorry, I've been going so fast. And this is a prediction for the annihilation luminosity per unit volume. And you can see, oops, sorry. You can see here that the annihilation luminosity is contributed almost equally by halos all the way from slightly bigger than the Earth, because they drop here because the concentration drops, but from halos in the mass range 10 to the minus 4 solar masses to 10 to the 12 solar masses, they all contribute about equally to the annihilation radiation. So the luminosity density is almost independent of mass in this mass range. And it's likely that most of the luminosity is actually coming from these tiny little halos of 10 to the minus 4 solar masses. And so previous extrapolations, they all get it all wrong, from factors ranging from 3 to 1,000. They're all wrong because nobody had been able to simulate objects of this scale. So not surprisingly, the extrapolations go wrong. So conclusions. 2 parts. One, small K crisis of CDM. One crisis. These are solved either by galaxy formation in the first 2 cases, by statistics in the third one, and baryon effects in the fourth one. And then sorry, I went too fast through these, but what I think I'm very excited about is the ability we now have to simulate halos, all halos that are occupied, all scales that are occupied in CDM. We can now simulate all the way from the mass of the Earth to the mass of galaxy clusters with equal resolution. And amazingly, all halos, maybe not amazingly since gravity scale free, have these universal NFW type profiles. And the concentration mass relation I show you is quite flat, except that it dips near the free streaming mass for reasons we could discuss. The mass concentration relation is independent of local environment, and it's likely that the annihilation luminosity is dominated by these very small halos and subhalos. So I'll finish here.